I'm going to show myself for just a few minutes, not longer, just so you know what I look like. But then as it happens, I still have a cold. I'm still sitting here wiping my nose with a rag. And so to save you the rather unpleasant side of me wiping my nose, I'm going to turn my camera off. So let's begin without further ado. Today we're going to be, in the second lecture, we're going to take the next step and look at what neural networks can represent. The topics for the day, we will see what neural networks can represent and what the restrictions are when we try to make them represent any specific function. And the restrictions will be in terms of depth, width, and activations. So for a quick recap, we've seen that tasks that were once considered to be purely in the domain of human expertise have been made possible by neural networks, also known as deep learning, like speech recognition, playing games, translation, and a whole lot more. In each case, the operation of the task can be thought of as this box which takes in some input and generates an output, like taking in a voice signal and generating a transcription or an image and its caption, or viewing a game state and predicting the next game state. Now, what's inside these boxes? What are these neural networks inside these boxes? Now, these are all functions. And a function where is anything that takes in an input and produces an output can be viewed as a function. And in a human being, these functions are computed by the human brain. And so, in their basic form, neural networks mimic the network structure of the human brain. We also saw in the last class that the brain is composed of networks of these little structures called neurons, these little cells called neurons. And the neurons have a specific structure. They have many little inputs, and they have outputs which go to other neurons. So each neuron is connected into by many neurons and connects out to several neurons. At a very high level, you can view the active action of the neuron as follows. The neuron receives inputs from several other neurons, and when the cumulative input exceeds a threshold, the neuron itself fires and activates downstream neurons. That's a very high level, crude kind of approximation of a neuron. But when you come up with that approximation, you can actually computationalize it in the form of a perceptron, where each perceptron obtains many inputs and computes a weighted sum of these inputs and compares that weighted sum to a threshold. If the weighted sum exceeds the threshold, it outputs a 1, otherwise it outputs a 0. Having defined a perceptron in this manner, then we can go ahead and emulate the larger structure of the brain by creating networks of these perceptrons. So here's the perceptron itself. It fires, each perceptron has several inputs. Corresponding to each input is a weight. And the perceptron fires if the weighted sum of all of these inputs, the weighted sum, exceeds some threshold T. And this operation is what electrical engineers will call a threshold gate. The threshold gate has many inputs. It computes a weighted sum of the inputs, and the outputs are 1 if the weighted sum exceeds a threshold, and a 0 otherwise. It's a very basic unit of Boolean circuits. Now, I can redraw the perceptron in this manner, as we saw in the last class. Instead of having the weighted sum be compared to a threshold, instead, I can say that what we compute is an affine function of the inputs, which is the weighted sum of the inputs plus a bias. So we end up with this affine value z. And now this affine value z is put through a threshold activation. A threshold activation is a function that outputs a 1 if the argument is non-negative and 0 otherwise. So this redrawing of the perceptron is exactly the same as this original figure. Instead of saying, summation wi greater than or equal to t, I'm computing summation wi plus b, where setting b equal to minus t would give you exactly the same equation as before. And then this value z is being compared to 0, right? And we also saw that once we redraw things like this, then we can do a few more things. Instead of having a threshold activation, we can have other functions in here. You can have any kind of squashing function. For example, a sigmoid. A sigmoid is a continuous and smooth version of a threshold, which goes to 0 when the argument is very negative, and 1 when the argument is very positive, and varies smoothly between the two extremities in the middle. But then it's not just sigmoids. You can have a tanh, which is basically a shifted sigmoid. Now, sigmoids and tanh are what are called squashing functions. It takes the domain, but the range is actually compressed. The output is always between 0 and 1. So the input can be from -infinity to +infinity. It squishes the whole thing down to lying between 0 and 1 for the sigmoid, -1 and 1 for the tanh. But you can also have other activations which are not squashing functions, like these ones to the right. This red line shows a rectification function. The output is identical to the input when the input is positive, and 0 when the input is negative. This blue line, what is called a soft plus, is a smooth version of the rectification function. So just redrawing this perceptron allows us to change the activation. For the rest of this lecture, however, we're going to mostly continue considering threshold activations, once again, because it makes explanations very simple and easy. So, but before that, what is the difference between an affine function and a linear function? We saw this in the last class. Anybody remember? What's the difference between an affine function and a linear function? Affine has an offset, right? So when you equate the function to 0, then if it's a linear function, the locus is going to go through the origin. Whereas if you have an affine function, then the locus, the function, when you equate it to 0, it could go through anywhere. It doesn't have to go through the origin. So a linear function is a special case of an affine function. Every linear function is affine, not every affine function is linear. And so with that said, let's release the first poll for the day. And let's see. Okay, 15 seconds, guys. Okay, I'm ending the poll. Now, does anybody want to tell me, is the first term a linear one? 3x plus 7y, is it linear? Yes. What about 3x plus 7y plus 4? Is it linear? No, because there's a plus 4. Is 3x plus 7y affine? Yes. It's 3x plus 7y plus a bias, where the bias just happens to be 0. And the last one obviously is affine. So you guys, almost everybody got all of the answers right. Right? Thank you. So fine. That's what we were. That's where we were. We left off in the last class. Let's continue. We're going to be discussing multi-layer perceptrons. What is a multi-layer perceptron? It's a network of perceptrons where the perceptrons may be arranged in a layer-wise manner, where you have perceptrons whose outputs are fed to other perceptrons, whose outputs are fed to other perceptrons. What is a layer? There's in fact a formal definition of a layer. We'll see that briefly. But first, this course is all about deep networks. What is a deep network? Does anybody know what a deep network is? There's a formal definition. Anyone? Depth greater than or equal to 3. Lovely. And how do you define depth? So here's how you define depth. In any directed graph with input source nodes and output sink nodes, depth is the length of the longest path from source to sink. So a source node is a node in a directed graph that has only outgoing edges. A sink node is a node that has only incoming edges. And so I have a path of length 1 from source to sink, but I also have a path of length 2. The depth of this graph is 2. In this graph, I have a path of length 1 from source to sink. I also have a path of length 2 and a path of length 3, but the longest path is of length 3. So the depth of this graph is 3. And so when I'm looking at neural networks, here I have a layer-wise neural network. If you look at the depth of this network, if I look at how many links, what is the maximum number of links to go from the input to the output, it's 1, 2, 3. So the depth of this network is 3. What about this one? What's the depth of this network? Anyone? 2. This one, 4. So you can see what depth means in terms of a network. A deep network is where the depth of the output, the depth of the output neurons is greater than 2. So this is a deep network. This guy on top right is not, because here you get to hop at least 3 links, or up to 3 links when you get to the output. Here you can get away with doing just 2. But then, what is a layer? A layer is the set of neurons that are all at the same depth with respect to the sink. So with respect to the input, not the sink, the source. I'm sorry, I should fix this error. Kelsey, please take a note. I should fix this. So in this network, this is the input. And all the neurons that have the same depth with respect to the input form a single layer. So can anybody point out which are the neurons which are layer 1 in this network? You can type or speak it. Anybody? So the source node is the leftmost, that's depth 1, is these are source. Here the length of the path is 0, right? So here's what I have. These guys are depth 0. The first layer are these 4 red nodes. They're all depth 1. These are the first layer. The 3 green nodes are all depth 2. They are the second layer. The third layer is just these 2 yellow nodes. They are depth 3. The longest path, although you do have paths of length 2, I believe, to these guys, the longest path to these 2 guys is 3. So these are the third layer. And the 2 output neurons, the blue ones, are all the fourth layer. So there are 4 layers over here, but visually what you would think of as a layer is not what is actually a layer. The layers are as they are colored here. And this network is deep because the depth over here is 4, which is greater than 2. So we understand what depth means now, right? And so we're going to discuss things in terms of depth. Now, a multi-layer perceptron is a network of perceptrons arranged layer-wise. We saw that in a multi-layer perceptron's input could be real or Boolean stimuli, and the outputs could be real or Boolean values. You can have multiple outputs for a single input. But what can this network compute? What kinds of input-output relationships can it model? We went through that as well. We saw that MLPs can compose Boolean functions. We saw that MLPs can compose classification boundaries. And we saw that MLPs can compose real-valued functions. The key term is can compose. But what are the limitations? Under what conditions can they compose these functions? That's what we're going to look at today. We're going to look at multi-layer perceptron functions and why we need depth. We are going to look at MLPs as universal classifiers and why we need depth, as universal function approximators, and again, why we need depth. And this is going to lead to a discussion of optimal depth and width. This last bullet here, RBF networks, is a wish list, which I always have. The slides are in the slide deck, but we won't be talking about it. Now, I must warn you that there are many more slides in the slide deck than I will be presenting in class. And the slides that are in the slide deck but not presented in class will still feature in the weekend quiz. So please download the slides and go through them, because the hidden slides will feature in the weekend quiz. So let's begin with the discussion of multi-layer perceptrons as universal Boolean functions. How well do MLPs model Boolean functions? We saw that individual perceptrons can model any simple binary Boolean gate. So this we saw is each input has a weight of 1. So this perceptron is only going to fire when both inputs are 1. This perceptron is a NOT gate. Whenever the input is 1, the total input is -1, which is less than 0, so it won't fire, and vice versa. And this we saw as an OR gate. The threshold is merely 1, so if either of the two inputs takes the value 1, the output is going to be a 1. So a perceptron can model any simple binary Boolean gate. But I told you in the last class that perceptrons are very powerful. They are far more powerful than simple Boolean gates. You can do something far more complex than that. So for example, here's a perceptron. This one will only fire if all of the first L inputs are 1 and all of the remaining inputs are 0. Under every other condition, it will not fire, meaning the output will remain 0. So let's see how that works. If all of the first L inputs are 1, then because all of these guys have a weight of 1, they are going to contribute a total input of L. If all of these guys are 0, because they're 0, they're going to contribute a total input of 0. So when you have L1s and the remainings are all be zeros, the total input is going to be L, which will match the threshold, and it will fire. If you turn off any of the first L, then the total contribution is going to become less than L, and so it won't fire. Similarly, if you turn on, switch, meaning set to 1, any of the inputs at the bottom, because these weights are -1, that's going to result in a net decrease in the total weighted sum coming into the perceptron, and it will not fire. So this perceptron is x1 ANDed through XL and not XL plus 1 ANDed through not XN. It only fires when these guys are all 1 and these guys are all 0. So you can put an arbitrarily complicated Boolean AND operation and compute it using a single perceptron. Is this making sense, guys? Yes or no? Yeah, okay. It's fairly easy, right? So here's another one. This one is going to fire if any of the first L inputs are 1 or if any of the remaining inputs are 0. Let's see how that works. Let's consider the one condition under which it will not fire, which is that all of these guys are 0 and all of these guys are 1. When all of these are 0 and all of these are 1, then these will contribute nothing. And these will contribute, because the weights are -1, you have n minus L of these guys. So they're going to contribute L minus n. And then if you switch, so that's one condition under which you don't want it to fire. So I add +1 to the threshold. Now, if you flip any one of these guys, then the weighted sum is going to match or exceed the threshold and it will fire. So it means that if any one or any one of these guys is 0, this neural perceptron is going to be fired, right? So what was the question? If x1 is 0 and yeah. So this is a universal OR gate, right? But then you can do something more fancy. You can get a majority gate. So you can say that this perceptron will fire if at least k of the inputs are 1. A single perceptron will perform this computation. If you want to do this using a Boolean gates, you will need an exponentially sized circuit, but a single perceptron can be made to perform this operation where it just checks if the total number of inputs is at least k. So, which means that you can compute an at least function, which means you can also compute a majority function. Are the majority of the inputs 1? So this is a generalized majority gate. And you can do other such very funky operations with perceptrons. You can compute fairly complex functions, Boolean functions, things that would require exponentially sized circuits if you were using simple Boolean gates. The perceptron can do something much more, do those with just a single perceptron. So it's a very powerful unit. Does this make sense, guys? How the majority gate works. And I want you to think about it, how you would do this using just ANDs and ORs, and you'd find that this is quickly going to become an exponentially sized circuit. But then we saw that a perceptron is not enough. It cannot compute an XOR. There's no setting of the weights that can make it compute an XOR. But once I connect up the perceptrons into a little network, they can compute the XOR. So this little network with 3 perceptrons has one perceptron computing, third one ANDing the two, and voila, I have an XOR. And in fact, my friend Gerald Friedland in Berkeley pointed out that I can get an XOR gate with just 2 perceptrons, which is this circuit. Now, how this works, I'll let you figure this out, but it's fairly simple if you want to visualize, if you try to plot it. But anyway, what that leads to is that once perceptrons can compute fairly complicated Boolean functions, but once you begin connecting them up, you can compute even more complex Boolean functions. And because perceptrons can emulate individual Boolean gates, MLPs can, in fact, compute any Boolean function. You give me a Boolean function, and I can construct an MLP that will compute it. So MLPs are universal Boolean functions. What this means is not that any MLP will compute any Boolean function. It means that for any Boolean function, I can construct an MLP that will compute it. Like this hideous function over here of 4 inputs is computed by this MLP. But then MLPs are universal Boolean functions. Any function over any number of inputs and any number of outputs can be computed by an appropriately constructed MLP. But in the examples that we saw, these perceptrons were connected up in many layers. So if I want to compute an arbitrary Boolean function, how many layers must the MLP have? What is the smallest number of layers I can get away with to compute any arbitrary Boolean function? Can anybody guess? Anyone? Just 2, right? 1 hidden layer. And so here's how. Any Boolean function is essentially a truth table. I can write it out like so. Here are all the input variables, and this is the output variable. And I can explicitly list out in table form all of the input combinations for which the output is 1. And implicitly for the rest of the input combinations, the output is 0. Now, so these represent input clauses, right? There are 6 input conditions under which the output of this function is 1. And you give me a Boolean function, it can be represented in this manner, right? It's essentially just a mapping from patterns of input to output. A truth table can be written as a disjunctive normal form formula, where you have 1 clause for each one of these rows in the table. So I have 6 clauses. The first clause over here says that the output is 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0. So it's not x1, not x2, x3, x4, and not x5. The second clause similarly says that the output is 1 if x1 is 0, not x1, x2 is 1, not x3, x4, x5. So 0, 1, 0, 1, 1. It's going to fire under that condition. This third clause captures this row. It's going to be not x1, x2, x3, not x4, not x5. And so corresponding to each of these rows, I can have 1 clause. And if any one, the pluses represent ORs. So if any one of these clauses becomes a 1, the overall function becomes a 1. Now this first clause is just a universal AND perceptron. And so I can capture it using a single perceptron. The second clause can be obtained using a second perceptron. Third one will be captured by third perceptron. 4, 5, 6. There are 6 clauses under which, there are 6 conditions under which this function will fire. And so I can just OR all of their outputs. And now I have expressed the entire function as a multi-layer perceptron with just 1 hidden layer, a total of 2 layers, but just 1 hidden layer. So what this means is that a 1 hidden layer MLP is a universal Boolean function. You give me a Boolean function, I can construct an MLP with just 1 hidden layer that will compute it. But how large will that layer get? To see how large it will get. So how large do you think it can get? The input layer is not a layer. There's no computation being done with it.
Depends on the number of ones you have in the Y column.
Yes, but what is the largest this can get? To see that, what is the largest number of perceptrons required in the single hidden layer for an n input variable function? We'll see how this goes. How many of you guys are familiar with Carnot maps? Have you heard of Carnot maps? At least the electrical engineers amongst you are familiar with it, right? So here is a Carnot map of 4 input variables. A Carnot map is a topological arrangement of variables. So here I have variables w, x, and y, and z. So here are the 4 possible combinations of w and x. Here are the 4 possible combinations of y and z. Now observe that the difference between any 2 adjacent rows is only 1 bit. You always just modify 1 bit. Similarly, the difference between any 2 adjacent columns is just 1 bit. Each cell over here represents a unique combination of the 4 variables. So this grid over here basically represents the entire truth table for 4 variables in a grid format. But then this has it's topologically arranged. Every cell is exactly 1 distant from all of its neighboring cells. And if you go to the boundaries, this cell over here, this first column is actually connected to the last column because the first and the last column also differ in only 1 bit. So here you see that this is 0, 0, and this is 1, 0. Similarly, the first and the last row differ in only just 1 bit. It's 0, 0, and 1, 0. So this whole thing can be thought of as an arrangement of the bit patterns with topological continuity. If you look at any 2 adjacent cells, they always differ in only 1 bit. And now in this grid, I can highlight all of the entries where the output must be 1. And so there are 7 entries where the output is 1 in this particular function. So if I just did a very basic standard naive DNF formula, that the DNF formula is going to require 7 terms. So the 1 hidden layer MLP is going to require 7 neurons in the hidden layer. But then I can begin grouping these things up. See that these 4 adjacent ones all give you the output 1. But that's a disjunctive normal form. That's this form, right? Where you have 1 clause per output, right? But now you can begin grouping these up. And so what this group tells us is that regardless of the value of w and x, so long as y and z are 0, 0, the output is 1. So these 4 group entries together can be collapsed into a single clause, not y, not z. Similarly, these neighboring guys can be collapsed. What the fact both of these are 1 means that that so long as w and x are 0, 1, and so long as y is 0, the output is 1. The value of z does not matter. So that's going to give you not x, y, but not w, x, not y, right? And similarly, these 2 corner guys can be collapsed and gives you this 3rd clause. In fact, I can collapse the 4 corners into 1 clause. And so this Carnot map can be constructed, this truth table, this Boolean function, can be composed using an MLP that has only 3 neurons in the hidden layer. And so by grouping things together, you can make the actual MLP much smaller than the truth table itself. But then, and so the size of the MLP sort of stays restricted. But then what arrangement of 1s and 0s over here simply cannot be reduced further? Checkerboard, right? There's no way I'm going to be grouping things together if they are in checkerboard format. And so in this case, if I want to compose a DNF or the most compact DNF formula, how many entries will it have over here? Anyone? 8, right? So this thing, because there are 8 combinations for which the output is 1 and they cannot be collapsed. And so the MLP is going to have 8 neurons in the hidden layer. Here's a three-dimensional version of a Cardinal map with 6 variables. So 6 variables will give you 64 combinations, but they're still arranged as a checkerboard. They cannot be collapsed. How many clauses will I have here? 32, right? A one hidden layer MLP is going to have 32 units in the hidden layer. So if I generalize it, if I have n inputs, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer. Is it making sense, guys? This one here? Right. So because you can't group things together. Every alternate pattern, if you arrange them topologically, is going to be a 1, and they can't be grouped together. So, which means that a one hidden layer MLP is going to need an exponential number of neurons. But then, does anybody recognize these functions? What are these functions? What do they look like? Before that, let me release the second poll. This. Oh, shoot. I killed the poll before I killed the poll. Someone else was releasing the poll and I killed it. All right, guys. So let's just take a poll. What is the answer here? Can anybody tell me? The answer is 512, right? With 10 inputs, you're going to need 512. Perfect. And so that tells us how this works. But then, what if we use multiple hidden layers instead of just one hidden layer? As many of you pointed out, these are just XOR functions. The first function is W XORed with X, XORed with Y, XORed with Z. The second one is U XORed with V, XORed with W, XORed with X, XORed with Y, XORed with Z. And so we also know that an XOR can be constructed using only 3 perceptrons. In fact, we can construct it using 2 perceptrons, right? And so here's how I can do this. If I have this function here, I can first compute W XOR X using 3 perceptrons. That result can be XORed with Y using 3 perceptrons. And that result can be XORed with Z using 3 more perceptrons. So if I have n variables, for n, I'm going to use I need 3 perceptrons for each XOR, and there are going to be n minus 1 XORs. And so in this case, I'm going to need 9 perceptrons. Here there are 6 variables, so there will be 5 XORs, 1, 2, 3, 4, 5. And so this network is going to require only 15 perceptrons, right? And what is the depth of this network? Over here. Anyone? It's going to be 2 layers per XOR. It's 10, right? By arranging the network in a deep, by the function in a deep network, an XOR of n variables will require only 3 times n minus 1 perceptrons. So a single hidden layer network will require 2 raised to n minus 1 plus 1 perceptrons. The plus 1 is for the output unit. So a single hidden layer network is going to be exponential in n in size. Whereas if I arrange the same function in a deep network, I'm just going to need 3 times n minus 1 perceptrons, which is linear in n. And so going from shallow to deep can change the size of the network required to express the function from being exponential in the inputs to linear in the inputs. How deep? We actually have a clear answer to that as well. Now, if I have n variables, that network can be arranged in just 2 times log 2 of n layers. How so? Now we know that the XOR is associative. So if I've got a whole bunch of variables that are being XORed, then I can begin XORing the variables pairwise, and then I can XOR the results, and then I can XOR those results until I get the final output. And because at each point I'm going to be XORing things pairwise, so what this means is that at each stage, the number of variables is going to reduce by 2. So the total number of stages is going to be log 2 of n. each stage has 2 layers, as shown by these highlighted ellipses. And so the total number of layers is 2 log 2 of n. Is this making sense? So here is it, right? Each of these is an XOR. Is this making sense? Right? So here's what it is. If I just use one hidden layer, I'm going to need a network that's exponential in n. But if I let the network be 2 log 2 n layers, the number of units is going to be linear in the number of inputs. So, which is a pretty remarkable result. But then something even more interesting. Let's say I limit the number of layers, but it's not, I let the layer network be deep, but I don't give you 2 log 2 of n layers. I say the network can only be 3 layers. What happens then? In the best case, my first stage is going to begin XORing all of these variables pairwise. Till over here, I get n over 2 variables. And then the rest of it is still an XOR, right? Because we saw that after XORing things pairwise, I'm still left with an XOR function. So if I have a finite number of layers subsequently, that one layer is going to be exponential in size. So if I only let this network be 3 layers deep, then after 2 layers, I'm going to get n over 2 variables. And then this hidden layer is going to be exponential in n over 2, which is exponential in n in width. So a network with less than 2 raised to the minimum number of layers required is going to require at least one layer, which is exponential in width. And if you try to say, I don't want this to be exponential, I'm going to have fewer neurons over here, that network will not compute the function that you want. And I'm using the XOR as a specific example because the XOR is a horrible function. If you miss one bit in an XOR, it's going to be wrong 50% of the time. So if I just delete one essential neuron from the circuit, that function is random. And so what we are saying, what we get over here is that the network, by reducing the number of layers below the minimum, we get an exponentially sized network to express the function. And a network with fewer than the minimum required number of neurons cannot model the function. Now, when you're writing software, we actually like to think in terms of parameters, not neurons. And the parameters of the network are the number of weights in the network. So the number of connections. In this example, there are 30. That's what really matters. But then networks that require an exponential number of neurons will require an exponential number of weights. So the logic still holds. So to recap, deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using only one hidden layer. Any questions? Questions? The biases can be thought of as yet another weight. So, any questions, guys? No. All right. So, in summary, an MLP is a universal Boolean function, but can represent a given function only if it is sufficiently wide and sufficiently deep, and depth can be traded off for an exponential growth of the width of the network. Optimal width and depth depend on the number of variables and the complexity of the Boolean function, where the complexity is defined in terms of the minimal number of terms in the DNF formula to represent it. So the story so far, MLPs are universal Boolean ML functions, universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. But a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function, and they could actually be exponentially smaller. So we've dealt with the issue of how do MLPs behave as Boolean functions, but then how about as class? Do things change when the input becomes real? Now, to recap, we saw that the MLP is really just a function over real inputs. It's a function that can find complex decision boundaries over the space of reals. We saw exactly how in the last class. We saw that assuming a threshold activation, a single perceptron is this Heaviside function. The boundary between where it outputs a 1 and where it outputs a 0 is a hyperplane, a line in 2 dimensions, where the weighted sum of inputs exactly matches the threshold. And so for 2 dimensions, if you actually plotted this function, it's going to look like the step function, where the boundary between the 1 and the 0 is this line. In general, it's a multidimensional Heaviside function. It's a step function. It's a linear classifier. But then we saw how a linear classifier gives you all the standard Boolean gates. So if the inputs were Boolean, then a perceptron which has a decision boundary like so is going to act like, what is this gate? Remember? What was this gate? This is an OR. This was a NOT, right? And this is an XOR, and you can see why a single perceptron cannot model it, right? Because a perceptron can go up, but that doesn't come back down. So here you have 2 boundaries, whereas a perceptron can capture only 1 boundary, which is why a single perceptron cannot compute an XOR. You're going to need multiple perceptrons, one for each of the boundaries, which you combine. So let me release the third pole. Guys, can you see the third pole? Which, yeah. I didn't need the 5 seconds. 34 students aren't responding, right? And what is the answer here? An XOR needs 2 hidden neurons and 1 output neuron, because we need 1 hidden neuron for each of the 2 boundaries and an output to AND them. That's basically what we saw from the figure, right? That's why it is true. Did this make sense? Did the logic here make sense to you guys? Perfect. Okay. So but then we saw we can compose complicated decision boundaries using the perceptron. For instance, if I want to compute a MLP which captures this pentagonal decision boundary, with the 1 being output inside and 0 outside, the way we would do it is we'd have 1 perceptron for each of these boundaries of the pentagon, 1 for the lowermost boundary. So this perceptron would output a 0 below the line and the 1 above. This one is going to output a 0 to the right of this line and 1 to the left. This one is going to output a 0 above this line and 1 below. This one is going to output a 0 above this line and 1 below. And this one is going to output a 0 to the left of this line and 1 to the right. And so when inputs go in and are evaluated by all 5 of these perceptrons, only for inputs within this pentagonal region will all 5 perceptrons output a 1. So if you compare their sum to a threshold of 5, this entire network is only going to fire if the input lies exactly within this pentagon and not otherwise. Outside the pentagon, at least one of these perceptrons is not outputting a 1. But once we know how to compute a pentagonal decision boundary, we saw how we could compose more complex boundaries like this one, a double pentagon. You'd have 1 subnet for the first pentagon, the second subnet for the second one, and then you can OR the 2, and then you get the more complex boundary. Or even more complex boundaries like these guys, like this crazy shape here, or this human-sized shaped boundary here, or this horse here. How would you do it? Let's take this one as an example. I can just decompose it into many little polytopes. I can have 1 subnet for each of the polytopes and then OR them up. And then I'm going to get a decision boundary, which is exactly this crazy decision boundary that I've got. So I can model pretty much any decision boundary. But this network actually requires 1, 2, 3 layers, right? And you can imagine that as you went into higher dimensions with more and more complex shapes, you might need more layers. But my claim is that you can also do this with just 1 hidden layer. Let me take this trivial example. how would you compose the decision boundary to the left with a circuit such as, with a network such as the one to the right, which has only one hidden layer? Does anybody think this is possible? Yes or no? You think you can do it? And how would you do it? Use different weights. What kinds of weights? A limit. Any thoughts, guys? How you would do this? Weights for the edges. Linear combination of all constraints. How many neurons do you think you would require in the hidden layer? It turns out you cannot if you have a finite number of neurons. Why? For this particular figure, why? Because if I have I have to capture 10 boundaries over here, right? And you're going to get interferences in these regions between the pentagons. And so you're going to, if I limit the number of units over here, you're always going to get some spurious regions where the network will output a 1 when you want it to output a 0. The way to do it is a little more sophisticated than that. And for that, I'm going to go back to a simpler shape. I'll start off with a diamond. So let's say I want to compose a bound network which gets this diamond-shaped boundary. So then, of course, I'm going to need four neurons, one for each of these boundaries. And the sum of the outputs of these 4 neurons is going to be 4 inside the pentagon, inside the diamond, and less than 4 outside. But then look at the sum just outside. In these yellow regions, the sum is 3. And in these white regions, the sum is 2. So here is a plot of the actual sum against the two inputs. And you can see that the sum actually has this crazy shape. And when I use a threshold of 4, I'm slicing it up here, which is why I get a diamond-shaped decision boundary. But if I use a threshold of 3 and sliced it here, I'm going to get something that looks like a plus. So now I cannot, if I go from diamond to a pentagon, now I will have 5 neurons. The sum will be 5 inside the pentagon, but there are many regions where the sum is just less than 5, right? So here the regions where the sum is 1 less than 4 are infinite in area. Here, the regions where the sum is 1 less than 5 is finite in area, those regions which are 4. And so here is the sum again, right? If I go from a pentagon to a hexagon, here is the sum against the inputs. And the regions where inside the hexagon, the sum is 6. But the regions where the sum is just less than 6 have shrunk in area further still compared to the hexagon itself. So here's a heptagon. Here I'm just showing the sum. And you can see something interesting about the shape of this function. That just outside the heptagon, the regions where the sum is less than, now the two limit cases are 6 and 3, right? So 6 is the highest sum, 3 is the lowest sum. And as you increase the number of sizes, the area where the sum is neither n nor n over 2 keeps decreasing. So here this is for a heptagon. Here this is for something with 16 sides. The sum is 16 here, the sum is 8 out here. And in all of these interesting regions, the sum is between 16 and 8. This is for 64 sides. So the sum is 64 here, the sum is 32 out here. And in between, you can see that area keeps getting smoother and smoother. This is with 1,000 sides. And so increasing the number of sides reduces the area outside the polygon that has where the sum lies between n and n over 2. Did these pictures make sense, folks? Any questions? Right. So in the limit, what do you think this is going to end up looking like? As I increase the number of sides to infinity. Someone said a volcano shape. Exactly, right? So this is what it's going to look like in the limit. There's actually a nice little formula for it, which I won't derive. And as n tends to infinity, you're going to get a perfect circle within which the sum is n. Then it's going to fall rapidly off to n over 2, just outside. And as the diameter of this becomes smaller and smaller, in the limit, this is going to begin looking like a perfect cylinder. So you can think of it roughly as the cylindrical shape. And so with a very large number of, when I'm trying to compose something that's approaching a circle, I'm going to have a very large number of neurons in the hidden layer tending to infinity. And the sum of their outputs, this sum over here, is going to have this shape. It's going to be exactly n within the inner circle and exactly n over 2 outside. If I add an extra bias term, it subtracts the n over 2. Then the sum is going to be exactly n over 2 inside the circle and exactly 0 outside. So this is what it's going to look like. Does this make sense? Right. So questions now? All right. If this makes sense, let me continue. In fact, there was a way of having you guys raise your hands so that I could see that it made sense to most of you. Can you just raise your hands if you get it the next time I ask? I'd appreciate that, right? So thank you. Now let me continue. So now suppose I want to get a perfect cylindrical decision boundary. I can just have a very large number of these guys, including this bias. It's n over 2 because I added this extra bias term, which subtracts n over 2. Did that answer your question? Right. And so now if I use a threshold of n over 2, I'm going to get a decision boundary, which is a perfect circle, right? But then suppose I construct 2 of these networks, one of which composes a cylinder in one location, and another one which composes a cylinder in a different location. And then I just simply sum up all of their outputs. The sum of this larger network is going to actually be 2 cylinders, because this subnet summed up to one perfect cylinder. This subnet summed up to another perfect cylinder. And outside the cylinder, this guy was 0. Outside this cylinder, this guy was 0. So when I sum their combined outputs together, I'm going to end up with 2 cylinders, because the region outside the cylinder, one cylinder, doesn't interfere and modify the values inside the other cylinder. And so this network with 2 subnets, each one composing a cylinder, is going to have, in this network, the sum of all of the neurons, outputs of all of the neurons in the hidden layer, is going to look like a double cylinder. And now, if I use a threshold of n over 2, I'm actually going to get a decision boundary, which is 2 disconnected circles. That makes sense? Right, raise your hands if this made sense. I'll wait for about 50 raised hands so before I can continue. So I know 20% of the class. Okay. So Sebastian here. This first subnet is this guy here. So if I look at the sum of the outputs of all of these neurons out here, that's going to look like a cylinder. Right, Sebastian? Just this first subnet. Similarly, I can have another subnet which composes a cylinder in a different location, right? And so when I sum the outputs of both subnets, it's going to be 2 cylinders. Why is it going to be 2 cylinders? Because outside the cylinder, this guy's producing a bunch of zeros. So these zeros, when they are added to the cylinder, they won't modify it. So the sums of the outputs of both subnets is going to be 2 cylinders. And then when I use a threshold of n over 2, this decision boundary is going to be 2 circles. And did that answer right? N is very large. It's going to be tending to infinity, right? So I could divide by n and make the whole thing and normalize it. But yes, you're absolutely right. And so now, if I want to compose this double pentagon using just one hidden layer, this is how I would have to do it. I'd have to fill it with an arbitrary number of circles. And I can make, to approximate it, I can make the approximation arbitrarily precise by making each of those circles smaller and smaller and smaller and packing them more and more closely. And so if you give me an error that you can tolerate, I can create a network that will have an error below that tolerance. But the point is, this is going to require essentially infinite neurons in the hidden layer. So a one hidden layer MLP can model any classification boundary, but it's going to require an absurd number of neurons in that one hidden layer. So even a one hidden layer MLP is a universal classifier. But then, as you can see, once I just begin adding a few more layers, the network becomes trivially small. Something that required an infinite number of neurons when I had just one hidden layer just needed, 13 when I allowed it to have 3 layers. So if I omitted only 2 in this case, I'd still need a very large number of neurons. So you can see how depth can essentially eliminate the requirement for width in this problem. So let's take another notion of, let's look at the notion of optimal depth in generic networks. We're looking at worst case decision boundaries for threshold activation networks. Now, a naive one hidden layer network, let's think of a network that must capture this decision boundary, which must output 1s inside the yellow regions and 0s in the gray regions. Now, as we just saw, if I want to do this with just a one hidden layer neural network, and if I do it naively, I'm going to end up requiring an infinite number of hidden neurons in that one hidden layer. But then if I allow myself to have 2 hidden layers, this is going to require only 56 neurons. How did I come about this number 56? That pattern is composed of 16 lines. So I can have the first hidden layer capture each one of these 16 lines. So this first perceptron, pardon me. So this first perceptron captures this first line here, this one, and it's going to output a 1 if the inputs are on one side and a 0 if the inputs are on the other side, and so on. Each one of these 16 perceptrons captures one of these 16 lines. Now there are 40 of these yellow regions. And once I have captured these boundaries, I can have 1 perceptron each for each of these yellow regions and then a final OR. So the total network is going to require 16 first layer neurons, 40 in the second layer, and a final OR in the third, 57 total neurons. But this pattern is just an XOR over the Ys. And so if I just used an XOR network after the initial set of Ys, there are 16 Ys, so there are 15 XORs to compute. And an XOR can be done with 3 neurons, as we saw, so this will require 61 neurons. But we also saw that an XOR can be done with just 2 neurons. So if I did this with 2 neurons, I'd need 15 times 2 neurons to capture the pattern, plus the 16 neurons for the initial 16 lines. So this pattern can be captured using just 46 neurons. So Alice, there are 16 lines. So I have 1 neuron for each of these lines. And there are 40 boxes. And each box is basically an AND of 3 or 4 lines. So I'm going to, And so I get 1 neuron for each of these yellow regions, and I OR the lot. Did that answer your question, Alice? Alice, did that answer your question? Yeah, okay. Thank you. So maybe the difference between 46 and 57 is not all that great. But then if I go to something more complex, this is a grid composed of 64 lines. where the network must output a 1 for inputs in the yellow regions. Then I'd need 64 first layer neurons for the first hidden layer neurons for each of the 64 lines. There are 544 yellow regions. So I'm going to need 144 neurons in the second layer, hidden layer, and the final output neuron. So there are a total of 609 neurons that would be required for this pattern. Now, if you think this pattern looks absurd, remember that in real life, you're going to be working in very high dimensions with extremely complicated patterns. This would actually be considered trivial compared to some of the decision boundaries that you will deal with in real life. And so this again is just an XOR, right? And if I just had my 64 neurons to capture the 64 lines, and then proceeded to build the rest of the network as an XOR, as a deep XOR network, then using 2 gates per XOR, this decision boundary can be captured using just 190 neurons. So going from 3 layers to many more layers actually decrease the number of neurons from 609 in this case to just 190. So if I wanted to do this with 1 hidden layer, it was infinite. With 2 layers, it was 609. But if I increase the number of layers, I could get away with just 190 neurons. So the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input. This is the worst case. Or exponential in the number of statistically independent features if you keep the network shallow. So from our perspective, this network is also shallow. It has only 2 hidden layers. But when you make it deep, the number of neurons and parameters required can fall extremely fast. So, story so far. Multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. They are universal classification engines. A network with a single hidden layer is a universal classifier. But a single layer network may require an exponentially large number of perceptrons compared to a deep one. Deeper networks may require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller. In other words, deeper networks are more expressive. For the same number of parameters, they can capture much more complicated functions. Any questions? Questions, anybody? Okay. Perceptrons, neurons, I'm using the same term at this point, right? So our perceptron is a neuron. So if everything so far was clear, please raise your hand so I can move on. So what I mean by expressive is that the complexity of the function that it can capture. Shallow network, the amount of computation is going to depend on the number of parameters, the number of neurons. And what we found was that if we want to use a shallow network, we're going to need a lot more neurons to capture the function accurately. And so, yes, for a certain degree of precision, the shallow network is going to end up requiring more computation. So for the same error, right? So in this case, both of them have the deep network and the shallow network both have 0 error, right? But the deep network just has far fewer neurons. Did that answer your question, Dongfeng? Right. So depth or width? Katrina, let's get to that question, right? So is there a good case for the use of a shallow network? And what is the input range of those 2 input neurons? So the input range is something that can be, we are not making any specific assumptions about the input. So there's no specific range, right? If you make the network deeper, all we are speaking of is the capacity of the network. If you make it deeper than required, it means that my network is more able to, is just as able to model the function. We just have more parameters than you need, right? Is width better because the computation is parallelizable? Now we're getting into practical regions. at this point, we're just speaking of what the model network can model, right? Exactly how we will do it is where we begin taking those judgment calls. But so let's get into that discussion again. But before that, and so that will be a topic of optimal depth versus width, James. We'll see that. We won't talk about the computation of it, aspect of it, but how these two can be traded off and how activations come into the picture. But for now, let's look at, yes, you're right, there would be redundant numbers. Let's look at the other aspect. We've looked at Boolean functions. We've looked at classification boundaries, classification functions. How about continuous valued regression? So we saw that if I want to construct a network to compute a continuous valued function of a single variable, there was a simple way of doing it. A simple 3-unit NLP with a summing output can generate a square pulse over the input. So this first unit is going to output, I'm using threshold gates again. This first unit is going to output a 1 if the input exceeds T1 and 0 otherwise. The second one outputs a 1 if the input exceeds T2 and 0 otherwise. I'm assuming T1 is less than T2 without loss of generality. And their outputs are summed with weights 1 and -1 respectively. So as the input goes from -infinity to +infinity, until the input arrives at T1, the net output remains 0. Between T1 and T2, the output becomes 1. And then after T2, the output is going to go back to 0. But once I can construct a network to get this little pulse, I can compose a network for an arbitrarily complex function by just slicing up the domain into little windows, within each of which I can construct, you have a 2-unit network which composes a pulse whose height is scaled to the value of the function or the average value of the function in that range. And so I can approximate the function. And I can make the approximation arbitrarily precise by making those little boxes narrower. So all of this is done using just one hidden layer, right? So what this means is that even a one hidden layer MLP can model an arbitrary function of a single input to arbitrary precision. Is this making sense? Because the activation there was not a threshold. So we're speaking of threshold activations. We'll talk about activations in a bit, right? So, okay. I'm assuming everybody is good with this so far, right? Okay. In this case, if I'm using threshold activations, then this is what I'm doing. On the other hand, if the activation function within the neuron itself is a sinusoid, then I don't need to be performing any approximation, right? So in the example that I gave in the quiz last time, the activation function within the neuron was sine of x. Whereas here, the activation function within the neuron is just a threshold activation. So to answer James, I haven't yet got to answer James' question, right? I'm not speaking of parallelizability at this point. That's not something we're going to be dealing with here. Right. Correct. And why are we going to go away from thresholds? Now, suppose I want to go to functions of higher dimensions than this guy. Then I can't just use the simple business of boxing up things and, partitioning the domain into little rectangular regions. There, I have to do something a little more tricky. We know that an MLP can compose a cylinder, which has a value of 0 outside a cylinder and n/2 inside. I can normalize it to have 1. You cannot use prisms. You will find that it doesn't work. This is how you would do it. You're going to have to do cylinders, and then I can take any continuous function and fill up the space below it with cylinders. So MLPs can compose arbitrary functions in any number of dimensions, even with only one hidden layer, as sums of scaled and shifted cylinders. And I can improve the precision by making the cylinders thinner. So even a 1 hidden layer neural network is a universal approximator. It's never going to get the function exactly, but I can make the error as small as I want it to be by making those cylinders smaller and more compact. Now, to answer why rectangular prisms wouldn't work, if I had access to a board, I could have tried to draw it, but it would take time. But you can try to work it out, and it won't actually work. So here's a poll, the fourth poll. Let's go back. And okay, I'll stop the poll here in 5 seconds. Okay, end poll and share results. And you guys seem to be split on the answers. So what do you think the correct answer is? Anyone? It's false. Why? It cannot be exact. It can only be approximate. That's exactly what we've been saying, right? So a real valued function can be modeled to arbitrary precision by a one hidden layer network with infinite neurons, but it's never going to be exact. There will always be some error. So you guys are good. It can only be approximate, right? So now let's get into this business of how depth and width can be traded off and how that interacts with the number of, with the activation function that you will be using. Now, in the previous discussion, we saw that a single hidden layer MLP is a universal function approximator. It can approximate any function to arbitrary precision, but may require infinite neurons. Deeper networks will require far fewer neurons for the same approximation error. So this is true for Boolean functions, classifiers, and real-valued functions. So this much, I'm assuming that I have managed to successfully convey, right? Again, raise your hands if you got this. I wait for 100 hands to be raised, so I have some degree of comfort that this makes that I haven't lost you. Okay, so Farhan, what do you want me to go over? So Farhan, I need what exactly do you want me to go over? So just the last part about the approximations. Guys, I only got 75 odd people telling me they got it. So, obviously I've lost you. But go to the Piazza thread for the lecture and ask your questions because I shouldn't be losing you, right? This is bad. So clearly there are some questions over here. So Farhan, did you get how I approximated the function over here? Can this approximation be exact? I'm filling up the function, but within each cylinder, there's always a flat region, right? Which is why if you give me any odd function, I can make the error smaller and smaller and smaller by making the cylinder smaller and smaller and compacting them together tighter and tighter. But there will always be some error. Did that answer your question? Right, perfect. Any other questions, guys? No, right? That's the difference between the infinity here of cylinders is a discrete infinity. The infinity of the function is a continuous infinity. The two are, one is much, much smaller than the other. So we're getting into a little bit of mathematical finesse over here, but it means that it doesn't matter how far you go, there's always going to be some error. I don't know if that answered your question, Ariane, but yes. That makes sense to you? It will approach zero. It won't become zero. That's like any limiting case. Right. So let's discuss sufficient width versus depth. Generally, deeper networks we saw will require far fewer neurons than shallow networks with the same error. But there are limitations, right? Aditya, that's correct. You're always looking at limits. So let's look at sufficiency of architecture. A neural network can represent any function provided it has sufficient capacity, meaning it's sufficiently broad and sufficiently deep to represent the function. And not all architectures can represent any function. So consider this network over here, this decision boundary over here. This decision boundary is composed of 16 lines. So I need 16 neurons in the first hidden layer to capture these 16 lines. And then I need 40 neurons, at least 40 neurons in the second layer to capture these 40 yellow regions, right? Now, instead of just having 16 neurons in the, and let's assume for now that I'm using a threshold activation. We're talking about the importance of depth, width, and activations. So now, instead of having only the full set of 16 neurons in the first layer, let's say I had only 8 neurons in the first layer. Can I compensate for it by having more neurons in subsequent layers and still get the same decision boundary? Anyone? Instead of having 16, I'm using threshold activations. Why not? No is the correct answer, but why not? You're losing information in the first layer, right? Perfect. Here's what will happen. A network with only 8 threshold neurons in the first layer might capture these 8 boundaries. But then when you get past this first layer, here is the only information that's left to you. It's going to tell you in which of these 1, 2, 3, 4, 5, 6, 7, 8, 9 regions the input lies based on the outputs of these 8 neurons. But within the region, you don't know exactly where you lie. And so there's nothing you can do subsequently to get the rest of the information required to form the various boundaries. So, Anand, the answer is slightly different from what you were thinking, right? Even if those 8 neurons captured these 8 boundaries, somehow, you're only going to be able to determine after the first layer, you only know exactly in which of these various regions the input lay, but the position within the region itself is going to be lost to you. And so there's nothing you can do by increasing or decreasing or anything else with the neurons in subsequent layers that can extract the remaining information. You will not be able to recover the decision boundaries. That makes sense to you guys? Question, guys? Yes. So the first layer, is it the most important? Let's get back to that, Sebastian. That's a very nice question, right? Now, the similar restrictions to apply to higher layers, regardless of depth. So here, for example, if I got the full complement of 16 neurons in the second layer, and I had only one more layer, but now I only put, say, 20 neurons in the second layer, would I be able to capture this boundary? Nope. So regardless of the depth, every layer must be sufficiently wide in order to capture the function. So not all architectures can represent every function. But then things get a little more interesting. The specific effect that we saw was because of the nature of the activation function that we chose. We chose a threshold activation. It gates information. So if I had only 4 neurons in the first layer, then this threshold activation function over here is going to, each of these neurons is going to capture one boundary, and it's going to output a 1 on one side and a 0 on the other side. So it's only going to tell you on which side of the boundary the input lies, but it doesn't give you any information about how far away you are from the boundary, right? And so, oh my God, I'm actually running over time. I didn't realize. My apologies, guys. I thought I had more time. So let me rush over this. Give me 5 minutes, right? So this effect is because we're using the threshold activation, it doesn't tell you how far you are from the boundary. But now suppose you had a sigmoid. A sigmoid is not a step function. The value continues to change continuously as you go away from the boundary. So it tells you how far you are from the boundary. And so now, if these neurons actually were sigmoid activations, then the outputs of these neurons will continue to have a little bit of information that subsequent layers could use to decide to improve your to learn the function properly. And again, a sigmoid is not a great activation because it's going to tell you how far you are from the boundary for a little while, and then it quickly saturates. Whereas if you were using something like a ReLU, then on one side of the boundary, it begins to give you accurate information about the decision from the boundary, distance from the boundary forever. So this is a more informative activation. If you were using activation functions like this green one, which has one slope to the left of this threshold and another to the right, it will continue to give you information about how far you are from the boundary on both sides of the boundary forever. And so narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded. But you'll require greater depth to permit later layers to capture patterns. So the lesson so far, MLPs are universal Boolean function approximators, can model any Boolean function classification or regression. Deeper MLPs can achieve the same precision with far fewer neurons, but must have sufficient capacity. And the activations must pass information through. Each layer must still be sufficiently wide to convey all relevant information from subsequent layers. I'm going to skip, I'll actually release this poll nonetheless. You guys can try it or not. And while you're looking at it, let me just go back to this key point that you can think of the threshold activation and the architecture under the threshold activation as some kind of a boundary condition. And then as you decrease the width of the layers from whatever limitation the threshold activation might have, your activation functions must continue to give you information about the decision and distance from the decision boundary. So if the activation function is sufficiently informative, you can make the layers narrower and hope that subsequent layers in the network will capture the missing information. So even then, even so, there is a limitation that, for example, if you were doing something like this, here, I'll stop the poll. Right? If you had a small number of neurons, you'd hope that the 8 neurons over here actually captured a grid and not something like this guy here, because if they align up parallelly, information is still going to be lost. So that's the end of the class. I'm ending sort of abruptly because I ran over time. This poll doesn't count. I just put this up on you can take a look. Is the first statement true? A network with an upper bound on the layer width can nevertheless model any function by making it sufficiently deep. Do you think it's true? No, it depends on the activation, right? Networks with graded activation functions are more able to compensate for insufficient width through depth than those with threshold or saturating activations. True or false? True, right? We can always compensate for limits in the width and depth of the network by using more graded activations. True or false? False. At some point, you're going to run into limits. For a given accuracy of modeling a function, networks with more graded activations will generally be smaller than those with less graded activations. True or false? True. Perfect. You guys are amazing. Thank you. We'll stop here. End of the class. I apologize for going 4 minutes over. And I'm here for a little time. We will take questions. I'll stop the recording.